All right, so this one, once I explain it, I think you'll realize it should be a super easy problem. Hi. And I bet if you read closely, I bet you could figure it out without knowing anything about the table. Just knowing the word maximum is all. So let's read carefully. It says the frequency table, and I'll tell you what all this stuff means, but let's just break it down and see if you can do it otherwise. It says summarizes 57 data values in the data set. Okay, I want you to read these 3 words. And that should point you to the answer. Because we have a category called data value, right? And so what is this asking for? Which is what? 14. Done. That's all it's asking. Okay? Now, a lot of students want to say 11. Why? Yeah, maybe they have the same number. But I'm guessing we're used to reading this as like an X, Y table. X and Y. It's actually not that, but that's how we're used to reading tables. And so we're looking at what's the biggest Y value. That's what I bet is probably the problem. But that's not actually what we do, because what this table is actually telling you is values of whatever data we collected, and then how many times do you observe that data, okay? So I want you to envision, let's say a student group of 57 students, okay? Maybe it's like a youth group. And these are their ages. And this is how many for each one. That's all this is, okay? So we have a total, if we add this column up, it's a total of 57 students. How many 8-year-olds are there? 8. Yep. How many 12-year-olds are there? 9. So that's this, okay? So the question is really asking, if we put it in the context of our story, what's the oldest student? Would be 14, right? So it's this side that we look for the maximum. What would it have to say if we were looking for the maximum of the right column? Yeah, something like that. Like what data value has the most, occurs the most times, or something like that. Cool. Does that help? Number 22 you probably haven't seen. Well, in fact, has anybody seen radians before? Okay. Have you ever, well, let me just show you. On your calculator, we have radian. If you get the cheap kind, like just the purse calculator kind, see where this says degree? Deg. You've probably seen that on one of those kind. Those aren't purse calculators, those are scientific, but you can change it to radians. So rad. Have you seen that? This one also has it says grad. You should put that like when you're graduating. Like, now it's good luck. Anyway, that's a different measurement altogether. But let's kind of talk through this, and I want to, in case this comes up on SAT, I want you to have this relationship known, but this problem doesn't require the depths of understanding of radians at all. Okay? It's actually more of a fraction addition problem, which we did a lot of in our probability unit. Okay. So, first of all, how are you used to measuring angles? Like if I said, what's the measure of this angle in a circle? What do we use mostly? Like how do we measure angles actually in general? Huh? Oh, okay. Well, I didn't mean necessarily with the tool, but you're right. What's on a protractor? If I said, what's the measure of that angle, what are you going to tell me? Degrees, right? So we use degrees. In this class, we use degrees more commonly. Okay. And I would say this is maybe like, I don't know, 50 degrees or something. Okay, if we did like Bailey said, we use the protractor. Well, radians is just another way to measure angles. Okay? It's like a different scale. It's like speaking a different language for the same thing. So if we say water versus agua, right? It's talking about the exact same thing, but it's just a different word. It's similar to that concept, where if I could measure this angle in degrees, or I could measure it in radians. And radians are way bigger than degrees are. Okay, I'll tell you more in a second. In a circle, how many degrees are there? All the way around a point, or how, like if we opened an angle all the way.
360.
Yep, okay. 360 degrees. We usually start, and this is more of a math thing, but when you have a circle, we start at, I'll put a line. Do this. We start here at the positive x-axis where it intersects the circle, and that's, sorry, do a better job here. That is 0 degrees. Okay, and then we start opening angles counterclockwise. Okay, so like this angle would be like 45 degrees. Okay? Alright. And then as we go all the way around, we're back to that point at 360 degrees. That's the whole circle. So what would the degrees be over here? 180, right? That's like the bottom, it's like half of a circle is your protractor. So your protractor goes from 0 to 180. Okay. Well, in terms of radians, it's a different measurement system. So we still go counterclockwise, all that stuff is the same, except for now, all the way around is 2 pi radians. Do you remember the value of pi? Yeah, so 2 pi is like just over 6. Okay, so I want you to process for a second. The whole circle has 360 degrees, but only just over 6 radians. So which is bigger, radians or degrees? Well, radians are way bigger, right? Like, it's like 1, 2, 3, 4. They're like big chunks of this circle, because there's only 6 of them. Anyway, we start with 0 radians, just like we do with degrees. Okay, so if it's 2 pi all the way around, how far is it to halfway? So what's half of 2 pi? Don't do decimals. Okay. I have 2 pi's. What's half of that? 1 pi, right? Okay, so this is pi radians. It's halfway around. Is everybody following so far? Okay, that's important for this problem. This is all that you really need to know about radians. If I went just vertically, what's this measure here of this angle? In degrees?
90.
It would be 90. Okay, if this is 1 pi to get to the other side of the circle, do you agree this would be 1/2 pi? It's like halfway to the pi. Okay, and then this would be 1½ pi. Okay, and then 2 pi. Now we do pi over 2, and this would be 3 pi over 2 is how we actually write it, but it's just 1½ pi. Anyway, we're just kind of counting by pi is how we end up doing it in radians. So really all you need to know is this. 2 pi radians equals 360 degrees. And that halfway around is 1 pi. Okay. That's all the pi knowledge, all the radian knowledge that you need to do this. The rest of it is fractions. So let's make this into an algebraic sentence. It says angle R is 2 pi over 3 radians. Angle T is 5 pi over 12 greater. What does greater mean to do? What did you say? Add, yeah. So 2 pi over 3 plus 5 pi over 12. Just add. How do we add fractions? We did that a bunch in probability. Need a common denominator, right? Like I'm not worried about the pi, that's just a number. So what is a good common denominator for these two? 12. How do we make, so that one's 12. How do we make this one 12? Awesome. So 8 pi over 12 plus 5 pi over 12 equals what? 13, yeah. 13 over 12 pi. Okay. That's all. Now we can answer our question because, look, this is multiple choice. Which of these degree choices is closest to this pi choice? Well, what is 13/12 really close to? In terms of like if we reduced it or even just divided it actually as a decimal. Don't do it, just think about it. It's super close to 1, isn't it? Like if that was 12/12 pi, wouldn't it be 1?
Yeah.
Okay, where is 1 pi in my circle? At 180. So which of these is it?
195.
It's 195, done. Because this is just barely over 1 pi, like 13/12 is just a little bigger than 1. And none of these other choices are even close to that. So, again, now that you've seen this, the process would be, hey, I know this is 2 pi radians. Pi is halfway, 2 pi is all the way. So, roughly how much of the circle is that? And then just pick your answer. Like if this had been, let's see if you can pick up on this. If this had been like, how about 4 pi over 9? What if we had added and got 4 pi over 9? What is that super close to? Like a number that you know instead of the 9, what would make that easier to do? Do you see how 4 over 9 is, it's pretty close to 4 over 8, which is what, if we reduce? Half. So if I said, what's the degrees of that, it would be real close to what degrees?
90.
It would be close to 90, right? It would be a little less, like maybe it would say 85 or something. Okay. So that was kind of one of the first ones that has had completely junior level work, because you don't usually get to this before Algebra 2, and sometimes you don't, actually often you don't even get to it in our Algebra 2 in our school because it's at the end. So, but how many radians are in 360 degrees in a circle? 2 pi. Next time you see pi, you're never going to think of it the same. All right, cool. I wanted to do that one with you guys because most of you are juniors and will be taking this test this year. In about, what is it, 2.5 months? Are you excited? Okay, on this one, first we know it's similar. I put these notations in there, but we know it's similar by what kind of angles are these and how do we know they're congruent? Yeah, those are corresponding, okay? If you remember our parallel, that's not it. Parallel lines unit, those are those corresponding angles are the angles that take the same position where I could slide that bottom line up and the angles would cover each other, okay? Anyway, that is also true on the left or on the right side. Those are also corresponding angles. And then we talked, I think yesterday, about the top one. Let's say you didn't see those, or maybe only thought of one of them. How do we know, or what do we know about the top? You guys remember that word from yesterday? Reflexive property? Okay, so we'll mark it with an X. Guys, it's a good idea, not required, but a good idea to draw these two triangles separately. Because I think it'll help you make less mistakes. So I have 30 and y and 14. And then in the big triangle, what do we have? Okay, 22.
30x on the right side plus x.
30 plus x, good.
And then 15 plus
15 plus
y.
y. Awesome. And then we can just, once we have that going, we can just make sure we're comparing corresponding parts, and then we can just set up a proportion. Braden, what did you use for x?
For x, I did 22 over 14, and then x over 30.
And then what?
X over 30.
Okay, so that doesn't actually work. So he said he did this. Do you see now with the separate pictures why it doesn't? Because we have to, like this side length that corresponds to 30 has to have that 30 plus added in there. Otherwise it's not corresponding. Okay. In other words, we're kind of comparing a piece of a trapezoid, this figure, to a triangle. So be careful on those. And so let's set this up. Remember to put 30 plus x in parentheses. And then, oh, that was weird. And then 22 times 30, what is that, 660, I think? Okay? Did you check? Did anybody check that? Did anybody get an answer for this? Uh-oh. 14 times 30, I think, is 420. Somebody should be checking my answers here. Alright, so 10. X is 10. Now what? How do you solve for y? Yeah, pretty close. Like, why don't you tell us, Bailey? What would you do?
I would just do 22 over 14 and then equals 15 plus y over just do y.
Yeah, that's good. Okay. And then this time we'll just have variables on both sides, but it's, in terms of solving process, it's kind of the same. Okay. Can someone check that? It's right, actually. Okay, so and then we get, so subtract your 14, you get 8y equals 210. And then y, that's not going to be a nice number. Let's do a decimal this time. Okay. Did anybody get y? No? Yeah? You did? Yeah. Just one of you? Okay, so what was the trouble on this one? Because yesterday you guys were, on these kind, you were kind of doing good, I think, if I remember right. Go ahead.
I just accidentally did the same thing that Brayden did.
Oh, okay, how about you?
I didn't realize those were 22s. They look like question marks from here, so that kind of threw me off.
Yeah, I could see that. If they had question marks. But in terms of setup, are we good on why this has to be 30 plus x and 15 plus y? Now we're good. Okay, are you good on that? Okay. We are going to talk about a theorem where we can relate 30 and x and y and 15 just directly. It's called the side splitter. Like if we cut the side and split it, then we can relate just side lengths. But as soon as we have to bring the bottoms in, that doesn't work. So that's why this one in particular had to be the way that we did it. All right, I think we'll do another couple of those, but let's see how this goes just for fun. That face.
Sorry.
How do we set up our proof? Let's just start there since it's been a little while.
8 minutes.
Yep. What comes first?
Given.
And let's talk about all this notation. What do those lines mean? Parallel. And that is barely shown in the picture, but I'll kind of emphasize it more. What do parallel lines typically tell us in stuff like this? Like, what are they? We're talking about lines, but really, what's it telling us about?
They're like similar and related. Or
Well, I don't know what you mean by related.
they like are perfectly identical from each other. Like
They have the same slope if we were graphing, but again, more specific to this kind of work, when we're told about parallel lines, it's telling us about angles, actually, right? Even though these are lines, AB and DC, it's actually, the intent is to tell us about angle congruence, right? With this whole thing, I always go back to the initial look that we did at parallel lines, and we had all the different angle relationships. So, like, what kind of angles are those two? You guys remember? Alternate interior. Those two. Also, these two. So those are congruent. So parallel lines would be telling us about those, maybe. Because they're useful, because they're congruent. And then we already talked about corresponding. So like those two are corresponding. So are these two, etc. Okay? Anyway, so it's kind of sometimes a little misleading because we're told about lines, but it's actually meaning to tell us about angles. So keep telling yourself that so you can try to keep it familiar. Okay, what does all this mean? Yeah, what is this symbol? Congruent, meaning exactly the same. So A, C, B, and E, those are already marked as congruent. Remember, in a proof, anything that's not marked, that was given, you want to go mark it. Okay? Alright. Remember, our options for proving similarity were these three only. So two angles congruent, two sides, I'll just say it that way, two proportional sides with an angle in between, that's congruent, and then three proportional sides. So if you remember back to these, the only way we could do either of the second two is if we were told something about the sides being proportional. So are we told that in this case? No. So what do we do? Like, which one are we shooting for? We weren't told anything is proportional. I just said that, right? So we can't use sides. So it's this one. Okay, we're going to go for that one. Because we know nothing about sides at all. Nothing. We don't know side lengths. We don't know proportionality. There's no way to do it that way. So angle is the only potential option. Well, we have one angle. So we're halfway there. What else do we need to finish, I guess is my question. We need another angle. Well, which angle do we know for sure is congruent because of what we are given at this point? Okay. I know where you're going with this. Except we can't say angle C because there are technically 1, 2, 3, and honestly the bottom is 1, 2. 4 angles there.
So it'd be angle DCE.
Awesome, good job. Okay, so specifically this one is angle DCE. So angle B is okay to say because there's only one angle there. And then DCE on the other side. And why are those congruent? What did you say?
Betty, which one? It's because we have our parallel lines and our angles.
Yeah, if we show these parallel lines, and here's our transversal, So what kind are those? Yeah.
Corresponding.
Good job. Those are corresponding. Okay. So far, we've only had to come up with one thing, right? And we're done. So what's the last line? Because we did angle, angle. So we are ready to conclude this proof, actually.
Triangle ABC. Similar to triangle DCE. Because of angle.
Cool. Everybody good on that? Anybody get there on your own? Yeah? Awesome. Is that a thumbs up? All right, cool. Guys, this was a little bit of a struggle, so we're going to come back to this, but after the break. So number 3 should have got 12. 5, you should have got 3. 7 should have got 13. Any of those you'd like to do? Yep.
Tell C1.
Well, if you did 1, you should have got 11. Yeah. Yep. Let's do it. So this is like the one just a bit ago, not the warm-up, but right after. X this time is on the bottom, so we can't just compare pieces, and we want to split this, let me draw that better, split this into a smaller and a bigger triangle. Okay, small has 7 and 7, and big left side has to correspond to the entire left side like the small one did, which is what?
Would it be 7 plus X? Or,
Well, just this left side, I'm saying.
oh, that'd be 13.
Yeah, or 12.
Or 12.
Okay. Excuse me, and then the bottom is just X. That's okay to leave it as X. Guys, have you noticed that it's really dependent on the pictures? Right? Like, how should I say that? I think, are you finding the solving, what I'm trying to say is, are you finding the solving to be going okay? It's really knowing how to set it up, right? That's what I mean. How would we set a proportion up for this one? Yeah. All right, and this one we don't really have to even do a proportion because what does X have to be? Like it has to match this value, so just like mirroring it, X has to be 12, right? If you set up a proportion and solve, it's fine, it'll still work, but make sure that it, really what we're doing when we do that is making sure the values are the same. Karen, did that help? Okay, what else? Any others? Which one? 5, okay. 5, there it is right there. Okay, anytime you have these triangles within triangles, you should be drawing them separate, is my suggestion. So, maybe up here. So we have that little top piece, and then we have the whole triangle. And what's the dimensions, like what should I label in the little one? Go ahead, Sylvan. Good. And then how about the left side of the big one? 16 is good, but do you see how 3 would be like, I would have to draw a trapezoid instead of a triangle? Yeah, 3 plus X. Because it's like saying, hey, measure 3 centimeters plus X more centimeters if we like pulled out our tape measure. So it's not times, but add. And then what's a good proportion to solve? Awesome. You guys are doing really well with the setup, or like the proportion stuff. So good job on that. Okay, so 16x, this diagonal, and then equals 8 times 3 plus x. from the other way. 16x is 24 plus 8x. Well, I just lost the 8 there. 8x. And then subtract 8x. And x is 3. Okay? Just for fun, I want you to try this. I want you to draw an 8 with your opposite hand that you normally use. An 8, yeah. It's hard, huh? Oh, that was with your left hand?
Yeah,
Wow, way to
I
go.
just concentrated really
Yeah.
hard.
So I had you try that because this is years ago. I had to have surgery on my right arm, which I'm right-handed, and so I couldn't teach with my right hand. And that first, I don't know, it was probably a week or two. I got up to write on the board and would write an 8, and it was like no connection to my brain. It was weird. Like I would just be, it would be like just dead, like nothing. It was really, really strange. But you did good. If you ever have to have surgery, you'll be good.
I can't write with my left hand though.
Oh, I know, it's tough. Do you feel a little more comfortable with these now? Because we are going to be using this a lot in the new section when we get there. So far, we're just kind of reviewing. Okay. So grab that blueprint. This is kind of interesting. Like in terms of similarity in the real world. Okay. And I can zoom this a little. What do you notice about this? Just anything. Just what do you notice about this blueprint? Okay. There's only one bedroom, you're right. What else?
There's a porch. Is that optional?
Yep. OPT would be optional, so if you wanted to build like probably a wood porch or even concrete, you know.
There's like a bunch of measurements outside, like all those squares on the top and bottom.
Yeah, all these measurements, right? So basically what those are telling you is like between these two lines is 7 feet, 7.5 inches. Okay, good.
All of the doors have like a little eagle, like sheet things to write everything.
Yeah, that arc. Yeah, so she's pointing out like these, the arc for the doors. Good job for seeing that they're doors. And that's telling you which direction also that the door should open. Instead of, you could put the hinges different where it would open out. But if you think about like if this door opened out, it would kind of block access, right? And then,
If they want to have an optional porch, then why would they have an optional front door?
I guess I'm not seeing that optional front door
Yeah, it's down there.
down there.
It says 36.
Oh, this you mean?
No,
No, where?
no, the one near the
To your left.
storage loft above thing, right in front of you.
Oh, there we go. Gotcha. I guess that's probably an optional, not an optional front door, but an optional side door to get out.
And where's the front door then?
It's right here.
Oh,
That would be designed as the front door to enter that narrow in.
who goes
Okay.
through their house, through their porch?
I do. Well, actually, we go in through the garage, but we have a deck on the front of our house, in front of the front door. What's this thing? That's the toilet, sink, yep.
That's
What
the
do you think?
bathtub.
Huh?
That's the bathtub.
Bathtub, thank you.
No, the one piece is the bathtub.
30 by 60.
Oh, yeah, I was right. That's a sink. That's the bath. Okay.
That's a kitchen.
What is that thing?
Another.
Yep, stove oven, kitchen sink. What do you suppose DW?
Drawer.
Okay. I think probably dishwasher, since it's optional, but cool. Well, so you notice all of the things that are going to be in there, and this is the water heater, By the way, that's probably the washer and dryer.
You have to have a refrigerator all the way. on the
Yeah, that would be a
opposite-
weird kitchen, wouldn't it?
On the opposite side of the kitchen.
Like, yeah, you'd constantly be walking across traffic. Remember we learned about the kitchen triangle, where it wasn't supposed to be that traffic was routed through the kitchen, so this would not work. But it's a pretty basic floor plan. Anyway, in all of these measurements are telling you how wide stuff is, or how, like, the dimensions of the bedroom and stuff. And then, okay, so look in this area of the picture. Why would that be offset right there? Like, why is there an inner dimension of 7 feet 7.5, and then an outer dimension of 8 feet 1.5?
The exterior of it,
Okay.
of the
So
wall.
yeah, so that's the thickness of the wall right there, right? Good. So people could take this plan, and these are legitimate building plans. You could build this place off of that. Now, not just this one. There's a whole bunch of other ones that go with it, but you could set this structure up based on these floor plans. Okay, and then I want you to look down here, right there. Oh, not do that. How do I get rid of this assistant?
Just click anywhere else.
Everything. Right there where it says scale. Everybody see that? Okay, so this is what we were kind of talking about yesterday. So what it's telling you is that on paper, 3/16 of an inch, which is about this big, it's small, represents what out in the real world? 1 foot. Okay? And so this drawing is drawn to scale versus most of ours in our class are not drawn to scale. Which means I could figure out the length of this door by taking how many 3/16 inches there are on paper. And it would literally translate into the length of the door in real life. And if I wanted to, I could say, hey, the door on paper is 2 inches or whatever. So if I wanted, I could say, hey, this wall is 4 or whatever, 6 or 7 door lengths long. And all of those comparisons would be accurate because it's drawn to an official scale. And there's a cool tool, you might have seen me have it up here yesterday, called an architect scale. It looks like a fancy ruler. And it has those scales on here. So, in fact, let me turn this on so you can see it. It's pretty neat. I hadn't learned how to do it until I was teaching, actually, because I never was exposed. Like in engineering, we had these, but we didn't use these scales. We had plans with, like, plans means like blueprints. They were big. We printed them on like this big of paper. It was cool. So of course, like a 200 page set of plans probably weighed like 20 pounds because it was like a roll. It was huge. Anyway, I didn't learn how to use one of these until more recently, which was kind of fun. I think it's neat. You'll have to let me know if you think you would like to try it at some point, because we can look at these again. Alright, there we go. So I need the camera mode. I hope this is helpful and interesting to you. Okay. Of course, finding the number that you're looking for. There it is. Okay. So you see on this thing, right there on the right corner, it says 3/16 scale. And since it's on the right side, I have to read the bottom numbers. Okay, so pick something that we know the measurement of. Like, how about the width of the living room? Okay, how wide is the width of the living room? This way. This way. 12 feet, 11 inches. So it's so cool because you can take this tool. Let's say that number wasn't on there, because sometimes your plans are all, there's so much information. We can take this tool, and I'll put it on the screen better once I get it lined up. Okay, do you see down there? Okay? So I start on 0 and then 12 feet and almost the next foot. So it's the paper is representing reality through this tool, which is pretty cool. So if you want to look at it, I'll leave it up here. But I just wanted you to have some exposure to how we use similarity in the real world. Like this stuff is every day. People are using a scale drawing to make something someplace. Does anybody's family work in construction? Yeah? Like what kind?
I guess it's more like before they start going in, they get the ground kind of.
Which still has this kind of stuff. How about yours, Braden?
My dad was a carpenter, or my stepdad was a carpenter, and I was a carpenter.
Okay. And you're doing this kind of stuff, aren't you? Have you dealt with blueprints and architect scales or whatever? Okay.
Just like this stuff.
Yeah. So it's pretty neat. Like I told you the other day, this is a scale model of a shed that we built off of blueprints using the architect scales. Like this, if you could like magic wand this to expand it up, it would be the exact dimensions of a real shed, like the one that it's made for. Okay, here's another way you can use this. I saw this on a YouTube. I can't remember what I was, or it wasn't a YouTube, it was an article. Somebody was using a picture to find the scale and actual size of something. So I've asked you if you heard of Robert Wadlow. I'm going to say Wadlow. I might be saying it wrong. That's what I'm going to say. Anybody heard of him? Okay. Here's a picture of him, or some pictures of him. In fact, let me turn the lights off. What do you notice?
He's very tall.
Very tall.
My God, he's almost taller than his entire house.
These are, I know we are used to in our modern world of modified pictures. These are not. These are real pictures. Like, look at his hands, you know, like, not only is it tall, but look how big it is too, right? Okay, I'll show you a few more.
He is very tall.
Yeah, weird, right? No, I promise these aren't doctored. I know it seems like they are.
It's unnatural how like tall he is.
Yeah, doesn't it? It looks,
I think,
there looks something like it's doctored, but it's not, huh?
I think I've heard of him before.
Okay. Yeah, I'll show you a few more.
Isn't it like a genetic thing?
Yep. What is it called? I'm not sure what the name. It was a genetic pituitary gland thing where he just kept growing. In fact, like in this one, you can tell he's young. That's his dad.
That's his dad?
Yeah.
I thought it was another kid.
No, that's his dad.
Oh my God. No, he looks like the dad.
Yeah, but by his face, he's probably early teenager.
And the other picture's old, kind of.
Yeah, older. Well, it's sad because he died at only age 22.
Yeah, I was gonna say, isn't that like,
I don't know.
He got an infection in his foot, and they couldn't treat it. This was 1940, so it's, you know, they still had good medicine, but not like now. Okay, there's his family.
does he have a wife?
No. Okay, it's interesting, like, think of a normal cane. Like, this cane is almost as tall as that woman. Like here would be his hand,
It's kind of scary, to be honest.
you know? I guess on his dad, his cane came up, like, to here. And that's, like, the bottom of his hand.
It's honestly kind of scary.
Isn't that crazy? Here's his chair. This is you can see the statue of him, so this is like a reproduction. But I mean, even that, like, it would be weird to have that sitting in your house as a thing that would have to accommodate somebody, right? This is like the size of you guys, that lady, I mean. Okay, shoe.
Holy moly.
Oh,
Jeez.
pretty wild, right?
Mm-hmm.
again, that's the statue, but this to me looks like an adult male foot, like probably like mine. And I think yeah, there's one with the dollar bill.
Wow.
So it's big in every dimension. If you go back to that one, like it's not just long, but it's just a huge foot, right? It's like a flipper. Okay, so how could we use similarity to figure out like how tall this guy is or how big his shoe is, maybe? I want you to think about that, and then we're going to try it. We have 10 minutes. We could at least figure out how big his shoe is in real life. Okay? So why don't you two guys work together, and then you two, and then you two? Okay? See if you can come up with the strategy. I'll leave the picture up here. See if you can come up with the strategy to use similarity. And proportionality is really what I'm saying, right? Proportionality to figure out the actual length of his shoe. And you'll probably need to come up here. That'll give you a hint. Now, one thing that's a little bit hard to tell in this picture is that it looks like this is a little bit rotated, which would foreshorten that section a little bit, right? So it may not be a perfect comparison, but that's okay.